Imagine you are standing in the middle of a massive cavernous cathedral.
Oh, that's a good visual.
Right. So the stone walls are like 50 feet high, the floor is solid marble, and the reverberation in there is absolutely out of control.
It's just a wall of echoes.
Exactly. Yeah. Every single footstep echoes for a solid 5 seconds. Now, imagine a friend stands 20 feet away and says your name. You hear it. You turn around. You recognize their voice instantly.
You probably don't even think about it. It just happens.
Yeah, you don't. But if you were to place a top-of-the-line, ultra-expensive studio microphone exactly where your head is and hit record,
Oh, the audio file would be a disaster.
like a complete, muddy, washed-out disaster of overlapping echoes. I mean, you wouldn't be able to make out a single syllable of your name. So the real question here is, why is your ear so much better than a perfect microphone?
Well, I think it comes down to a fundamental misunderstanding of what hearing actually is.
How so?
We have this really deep-seated assumption that our ears are just passive receivers, like a microphone diaphragm that just vibrates, sends an electrical signal down a wire, and hands the brain a perfect, objective recording of the physical air pressure in the room.
Yeah, we think of it as a totally linear process. Sound in, sound out. It's comforting to believe we are getting an unedited feed of reality.
It is comforting, but it is entirely wrong. The biological reality is that your auditory system is not a microphone at all. It is an active, highly predictive, fiercely aggressive sculptor of reality.
A sculptor of reality. I like that.
It's true. I mean, it is constantly morphing, delaying frequencies, suppressing unwanted noise, and calculating mathematical derivatives before you even consciously register that a sound has occurred.
Well, welcome to today's deep dive. We are taking you on a journey into the hidden, microscopic machinery of your ears and your brain.
It's a fascinating space to explore.
It really is. Our mission today is to pull back the curtain on this biological illusion. We want to understand the exact mechanisms, the physical fluid dynamics, and the neural calculations that allow you to hear a pitch that doesn't actually physically exist. Yeah. Or how you can pinpoint the elevation of a bird chirping based on microscopic timing differences.
And to do this, we are delving into a treasure trove of research from the 14th International Symposium on Hearing.
Right, which was held in Kloppenburg, Germany back in 2006.
Yes, it was a monumental gathering. It brought together the absolute heavyweights of psychophysics, neurophysiology, and computational modeling.
It's essentially the world summit for people who want to reverse engineer the ear.
Exactly.
And to set the stage for you today, we are going to trace the pathway of a sound wave chronologically. We are going to start at the physical mechanics of the inner ear, the cochlea.
Then we'll follow the signal as it translates into electrical spikes traveling up the auditory nerve.
Right. And finally, we'll hit the brainstem, specifically the complex relay stations of the cochlear nucleus, to see how the brain begins to sort all this chaos.
By the time we are done, you will view your own ability to listen to music or hold a conversation in a crowded room as an absolute marvel of biological engineering.
Okay, let's unpack this. Let's start right at the entry point, the cochlea, the inner ear. We really need to visualize this first.
Right, the anatomy is crucial.
So it looks like a tiny snail shell embedded in the bone of your skull. If you were to unroll that snail shell, you'd basically have a tube filled with fluid, and running down the middle of that tube is a membrane. The basilar membrane.
That's the perfect visualization. Now, when a sound wave enters your ear, it pushes against a tiny window on that cochlear tube, and that creates a physical wave in the fluid.
Like dropping a pebble in a pond.
Sort of, yes. That fluid wave travels down the basilar membrane. But this membrane is not uniform. It's actually stiff and narrow at the entrance, and it becomes wider and floppier as it goes toward the apex.
Like a harp, right. Short, tight strings at one end and long, loose strings at the other.
Very much like a harp. And because of those varying physical properties, different frequencies of sound cause the membrane to vibrate most strongly at different physical locations.
Okay.
High frequencies kick right at the stiff base almost immediately upon entering, but low frequencies have to travel much further down the fluid, all the way to the floppy apex before they peak and trigger a nerve to fire.
Wait, so if a sound enters my ear that contains both high and low pitches, they don't reach the brain at the exact same time. There's like a biological lag?
Yes, exactly. It is called cochlear delay. High frequencies are processed almost instantaneously, but low frequencies are significantly delayed because they literally have to travel further through the physical medium of the cochlear fluid.
The brain gets the high parts of a sound before the low parts.
It does.
That feels incredibly counterintuitive. I mean, if I hit a drum, the thump and the crack happen simultaneously in the physical room. but my brain receives them staggered.
It receives them staggered, yes. And to understand exactly how our brains deal with this staggered delivery, a team of researchers, Otto Gleick, Marjorie Leek, and Robert Dooling, set up a really fascinating experiment comparing completely different species.
Right. They looked at mammals, like gerbils and humans, and compared them to birds, specifically canaries and zebra finches.
This comparison is crucial because mammalian ears and avian ears are physically constructed in vastly different ways. As you mentioned, mammalian cochleas are coiled and relatively long.
Human cochleas are pretty long, right?
Quite long, yes.
Mhm.
But a bird's inner ear, which is called the basilar papilla, is very short and it's completely straight. It doesn't coil at all.
But birds are incredibly good at hearing complex songs. So despite having completely different hardware, their behavioral performance in hearing tests is often remarkably similar to ours.
Right. So to figure out how the physical length of the hearing organ changes the way these animals process the timing of sound, the researchers decided to test them using something called Schroeder complexes.
I was looking at the spectrograms of these Schroeder complexes in our sources earlier. They look like a dense, repeating wave. But I need you to break down what they actually sound like and how they are built because it's so vital to the experiment.
A Schroeder complex is essentially a mathematically constructed sound. It is a harmonic complex, meaning it has a fundamental frequency like a lowest note and a series of overtones built on top of it.
Okay, think of it like a rich synthesizer chord.
Exactly. But the researchers do something very clever with the timing or the phase of those individual overtones. By precisely adjusting the phase of each harmonic, they create a sound where the instantaneous frequency sweeps either from low to high or high to low over and over again very rapidly.
So within a single second, the sound might do a microscopic whoop, 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 sweeping upward or a pew, pew, pew sweeping downward.
That's exactly what it sounds like. And they control the direction and the steepness of that sweep using a mathematical parameter called a scalar.
A scalar.
Right. The scalar ranges from negative 1.0 to positive 1.0. If they use a negative scalar, the sweep goes upward from low to high. If they use a positive scalar, the sweep goes downward from high to low.
Okay, so they have a tool to instantly blast an ear with a sweeping sound. And this is where it connects back to that delay in the cochlear fluid we were talking about. Because if you have a sound that naturally sweeps from low frequencies to high frequencies, the low sounds are physically entering the ear slightly before the high sounds.
You're touching on the exact mechanism they were testing. Let's look at how the auditory nerves react. When they played these sweeping sounds to the animals, they measured something called the compound action potential, or the CAP.
What is a CAP, like in physical terms?
Imagine placing an electrode near the auditory nerve bundle. The CAP is simply the electrical sum of all the individual nerve fibers firing at once.
Okay, so a total voltage.
Right. If the nerves fire randomly, the overall electrical voltage is low and messy. But if thousands of nerve fibers across different frequency regions fire at the exact same millisecond, you get a massive synchronized spike in voltage. That's a high SAP amplitude.
So it's like a staggered racetrack.
Exactly.
Yeah. The low frequencies are the runners on the outside lane. They have the furthest distance to run because they have to travel all the way to the apex of the cochlea.
Ah, I see.
And the high frequencies are the runners on the inside lane. They just have to step over the starting line at the base of the cochlea.
I really like this analogy. Let's play it out.
Well, if you shoot a normal starting gun, just a click, where all frequencies play at once, the inside lane finishes instantly, and the outside lane finishes a few milliseconds later. The crowd cheers at completely different times.
Right.
But if you use a negative Schroeder sweep, you are staggering the start times.
Yeah.
You let the low frequencies, the outside lane, start running first. Then, a fraction of a millisecond later, you let the high frequencies start. If you time the sweep perfectly, the low frequencies arrive at the apex at the exact same millisecond the high frequencies arrive at the base.
And that is precisely what the researchers found. When they played the negative scalar sweeps, the low to high sweeps, the stimulus physically compensated for the natural delay of the cochlear fluid.
Wow.
It resulted in a massive synchronized CAP. All the nerves fired simultaneously. But when they played the positive sweeps high to low, it exacerbated the delay, making the nerves fire at entirely different times, resulting in a very weak CAP.
But here's the kicker. The length of the racetrack isn't the same for every animal.
Right, and this is the beauty of the paper. Because human cochleas are very long, our mechanical delay for low frequencies is quite substantial. So to get all our nerve fibers to cross the finish line at the same time, we need a specific slower sweep.
which is a scalar of roughly negative zero point 0.2.
Yes. When a human hears that specific sweep, it perfectly synchronizes the firing across about 9 millimeters of our organ of Corti. That's almost a third of our entire hearing organ firing in perfect unison.
But a bird's basilar papilla is tiny, so their outside lane isn't nearly as long.
Exactly. For a bird, a sweep of negative 0.2 is entirely wrong. Their optimal sweep is much faster, corresponding to a scalar of negative 0.1.
Oh, wow.
And because their ear is so small, that specific sweep synchronizes about 2 millimeters of their papilla, which is actually 70% of their entire hearing organ.
So what does this all mean for you, the listener? It means the physical dimensions of your skull, the actual length of your inner ear tube, fundamentally alters the timing of how sound interacts with your brain.
It really does.
A sound that hits a bird's brain in perfect synchronization hits your brain entirely out of sync. Your reality is smeared by your own anatomy, and your brain just accepts that smearing is normal.
It's mechanical filtering at its most primal level. The geometry of the fluid chamber dictates the neural firing, but the inner ear is doing far more complex things than just delaying a signal. Delay is, well, it's passive geometry. The ear is also actively aggressive. It changes its own behavior based on what it hears.
This moves us from the shape of the ear to the biological volume knob, which is what Volker Hollmann and Birger Kohlmeier explored in their paper on the nonlinear auditory filter bank.
Yes.
To understand why their work is so important, I think we first need to understand how engineers used to think the ear worked.
For a very long time, the dominant model of the ear was a linear filter bank. If you've ever used a graphic equalizer on a stereo system or in a music app, you know what this looks like.
Sure.
You have a series of sliders. One slider controls the 500 hertz baseband, another controls the 1000 hertz midband, and another controls the 4000 hertz treble band.
Right, so the assumption was that the cochlea acts like a biological equalizer. You have a patch of hair cells for 500 hertz, a patch for 1000 hertz, and they just passively capture whatever energy falls into their specific lane.
That was the assumption. But that simple linear model completely fails to explain a physiological phenomenon known as two-tone suppression.
Okay, I'm stuck on this concept. Let's set up a scenario. Let's say I'm in a laboratory wearing headphones. You play a pure 1000 hertz tone for me. It's a clear, steady beat.
Okay.
And I have an electrode monitoring the nerve fiber in my ear that is tuned specifically to 1000 hertz. It's firing away happily, registering the tone. Then, without changing the volume of the 1000 hertz tone at all, you introduce a second tone, a low, rumbling 400 hertz tone into the headphones. What happens?
In a linear model, the 1000 hertz nerve fibers shouldn't care at all. The 400 hertz tone should activate the 400 hertz nerve fibers, and the 1000 hertz fiber should just keep doing its job.
Right, they're different sliders.
But in a living biological ear, if that 400 hertz tone gets loud enough, the nerve fiber tuned to 1000 hertz suddenly starts firing less.
But less.
Yes. The physical volume of the 1000 hertz sound in the room hasn't changed, but your ear's response to it drops dramatically. It suppresses the tone.
Wait, how is that physically possible? How does the 1000 hertz region of the cochlea even know that a 400 hertz tone is playing, let alone know to turn down its own sensitivity?
This is the crux of Hollmann and Kohlmeier's model. They realized that you can't just look at the average energy coming into a filter. You have to give the filter a brain. You have to track the instantaneous frequency.
What is instantaneous frequency as opposed to regular frequency?
A standard frequency analysis, like a Fourier transform, takes a chunk of time, say 10 milliseconds, and averages out what pitches were present during that window. But instantaneous frequency looks at the wave moment by moment, essentially calculating the derivative of the phase of the signal.
I need an analogy here. Derivative of the phase sounds like a calculus nightmare.
Let's try this. Imagine you are tracking a car driving down a highway. A standard frequency analysis just calculates the average speed of the trip, let's say 60 miles per hour. But instantaneous frequency tracks the micro adjustments of the steering wheel and the accelerator at every single millisecond. It tracks the momentary physical state of the system.
Okay, so applying to the ear.
Applied to the ear, imagine a single spot on the basilar membrane. Let's say the spot tuned to 1000 hertz. Every spot has a best frequency. Hollmann and Kohlmeier's model states that if the instantaneous frequency of the physical vibration hitting that spot deviates too far from its best frequency, the ear mechanically alters its own gain and compression.
Meaning if the fluid wave washing over the 1000 hertz spot is actually being driven by a massive 400 hertz sound wave, The instantaneous physics of the push and pull on the membrane are just wrong for that spot.
Exactly. And physiologically, researchers believe this comes down to the microscopic architecture of the outer hair cells. These are tiny cells sitting on the membrane, and they have microscopic hair-like structures called stereocilia sticking out of them.
These are the cells that actually amplify the sound, right? They physically dance and bounce to make quiet sounds louder.
Yes, they are a biological amplifier, but the physical direction that those stereocilia bend is critical. Studies suggest that when a 1000 hertz wave hits the 1000 hertz spot, it pushes the fluid in a way that bends the hairs at the perfect optimal angle to trigger the amplifier.
Okay, that makes sense.
But when a loud, rumbling 400 hertz wave crashes through that same area, the fluid dynamics are different. It pushes the hairs at a suboptimal angle.
So it's like trying to push a swing perfectly straight versus pushing it from a slight angle. If the 400 hertz wave hits the 1000 hertz hairs sideways, the hairs can't amplify the sound efficiently. The gain drops. The volume knob turns down.
That is a phenomenal way to visualize it. The loud off-frequency sound mechanically sabotages the amplification process for the on-frequency sound, and Hohmann and Kollmeyer's computational model replicated this behavior perfectly. It matched the psychophysical data showing how suppression grows incredibly rapidly, sometimes dropping the effective level of the suppressed tone by 2.5 decibels for every single decibel increase in the suppressor tone.
That is a massive drop. The ear is aggressively shutting down to protect itself from the loud rumble. But why does this matter in the grand scheme of things? Why build a computational model of this?
Because if we can mathematically model exactly how a healthy human ear suppresses noise on a millisecond by millisecond basis, we can embed that math into a microchip. This has massive implications for hearing aids. Current hearing aids often struggle with background noise because they just compress and amplify broad bands of sound. But if a hearing aid could track the instantaneous frequency of an incoming signal, it could act like a healthy outer hair cell.
All right.
It could dynamically enhance the specific frequencies of a person's voice while momentarily suppressing the off-frequency rumble of a passing truck, mimicking the ear's natural two-tone suppression.
We are literally copying the ear's proprietary volume knob to build better tech. But this raises a huge experimental problem. If the ear is constantly morphing its own gain, turning itself down when noise is present, how in the world do scientists ever measure its baseline sensitivity? You can't measure the sharpness of a filter if the filter changes shape the moment you test it.
You've hit on the exact paradox that drove the research in our next paper by Unoki, Miyauchi, and Tan. They set out to estimate the true, unadulterated tuning of auditory filters. They wanted to know how sharp our hearing actually is before the suppression kicks in.
How do you isolate something that is always morphing?
You have to play a game of acoustic hide-and-seek using a technique called notched noise masking.
Walk me through the physical setup. If I am the test subject, what am I hearing?
You are sitting in a soundproof booth. You hear a continuous blast of static white noise. But the researchers have carved a notch of silence out of the middle of the static. So you hear high-frequency hiss and low-frequency rumble, but there is a gap in the middle.
Okay, I hear the static of the hole in it.
Now, they play a pure, gentle tone right in the exact center of that silent hole. Because the tone is in the silent zone, you can hear it clearly. But then, they slowly start closing the hole. They make the notch narrower and narrower, bringing the static closer and closer to the pure tone.
Like walls closing in on the note.
Precisely. And at a certain point, the static gets so close to the tone that the tone completely disappears. It is masked. By recording the exact width of the notch at the moment the tone disappears, researchers can mathematically map the shape of your auditory filter.
But wait, if they're playing the static and the tone at the same time, wouldn't the static trigger the two-tone suppression we just talked about? Wouldn't the noise physically turn down the gain of the tone they're trying to measure?
Yes, and that is the problem with what they call simultaneous masking. If the noise and the tone play at the exact same time, the noise outside the notch activates those suboptimal stereocilia deflections.
It pushes the swing sideways.
Exactly. It turns down the gain of the outer hair cells. It blunts the filter. So if you use simultaneous masking, you measure a relatively wide, blunt auditory filter. But Unoki and his team wanted to see the filter without the suppression, so they used a second technique, forward masking.
How does forward masking separate them?
In forward masking, you play the static with the notch. But then you completely turn off the static, and a few milliseconds later, in the brief silence that follows, you play the pure tone.
If the static is gone, how is it masking anything?
Because the auditory nerve doesn't reset instantly, there is a lingering neural fatigue, a refractory period. The static essentially leaves a temporary shadow of deafness. If the tone falls into that shadow, you can't hear it. But, and this is the crucial part, because the static is physically turned off when the tone plays, the fluid in the cochlea isn't being pushed sideways anymore, the mechanical suppression is gone.
So the outer hair cells are free to provide maximum amplification for the tone.
Exactly. And the findings were striking. When Unoki's team measured the filters using forward basking, they found that the human auditory filter is significantly sharper and more precisely tuned than previously thought, especially at high frequencies and quiet sound levels.
To prove this was actually happening, they used something called the parallel Rho-X filter model. We need to define Rho-X because it sounds like a prescription drug.
Rho-X simply stands for rounded exponential. It's just the mathematical shape that engineers use to draw the curve of the filter, but the parallel part is what matters. They modeled the ear not as one filter, but as two parallel filters working together. One is a broad, passive filter, the tail. This represents the basic, unamplified mechanical vibration of the basilar membrane.
Okay, and the other one?
The second is a narrow, highly active filter at the tip. This represents the amplification of the outer hair cells.
So they essentially built a digital twin of the cochlea that separates the raw biology from the active amplifier.
Yes, and their modeling was so meticulous that they even accounted for physical ringing. In forward masking, even though the noise is turned off, the basilar membrane has physical mass. It continues to physically ring for a millisecond or two, like a bell. Unoki's team calculated how the decayed ringing of the noise might bleed into the time window of the tone and cause a tiny fraction of simultaneous suppression.
That is absurdly precise. But the ultimate takeaway here is profound. The simultaneous noise triggers a suppression effect that essentially widens your biological filter. Your ears are dynamically blunting their own precision based on the acoustic environment you are standing in.
Yes, exactly.
If you are in a quiet room, your hearing is razor sharp. If you step onto a noisy street, your ear physically morphs, widening its filters to handle the barrage of energy, sacrificing precision for survival.
It is a remarkable adaptation. So, at this point in our journey, we have a signal that has been temporarily delayed by the physical racetrack of the cochlea, aggressively compressed by the instantaneous frequency trackers, and dynamically sharpened and blunted by the acoustic environment. But filtering a sound is only half the battle.
Right. Because how does the brain take these isolated neural spikes from different parts of the cochlea and stitch them back together to understand a musical note?
Exactly.
If I hear a cello play a note, my brain doesn't say, oh, I detect energy at 200 hertz and 400 hertz and 600 hertz. My brain says that is a single note. That is a low G. How do we hear pitch? Which brings us to the research by Leonardo Sedolin and Bertrand Delgout, and one of my absolute favorite auditory illusions. The missing fundamental.
The missing fundamental is the ultimate test for any theory of pitch perception. If you want to understand how the brain works, you have to look at how it breaks, or rather, how it compensates. Let's explain the illusion.
If you sit at a grand piano and strike the note middle C, which is roughly 261 hertz, your ear obviously hears that frequency. But a piano string doesn't just vibrate as one giant jump rope. It vibrates in halves and thirds and quarters. So it also produces harmonics, overtones at multiples of that fundamental. You get energy at 522 hertz, 783 hertz, 0.54 hertz, and so on.
Correct. The fundamental gives the note its pitch, and the harmonics give it its timbre, its character.
But if you record that piano note into a computer and you use a digital equalizer to completely delete the 261 hertz fundamental, you completely erase the physical sound wave of the main note, but you leave the 522, 783, and 244 harmonics playing. Your brain still hears the pitch as 261 hertz.
It does.
Even though that physical frequency literally does not exist in the air anymore.
The brain interpolates the missing data. It looks at the harmonic pattern and deduces the fundamental. But the question is how the nervous system performs this computation. For decades, the scientific community was split into two camps, championing two different models, the rate place model and the interval model. Both have severe flaws.
Let's dismantle them. Start with the rate place model. How is that supposed to work?
The rate place model relies entirely on the physical map of the cochlea. Remember, different frequencies peak at different places on the basilar membrane. This model suggested the brain simply acts like a security guard looking at a bank of monitors. The brain looks to see which specific nerve fibers, which places are firing the fastest.
Okay.
If the fibers at the 522 Hz place, the 783 Hz place, and the 1044 Hz place are all firing rapidly, the brain's pattern recognition software says these are all exact multiples of 261. Therefore, the pitch is 261.
That sounds incredibly logical. Why is it wrong?
Because of a biological limitation called saturation, nerve fibers have a speed limit. They can only fire so many times per second before they max out. As the sound gets louder, more and more nerve fibers reach their maximum firing rate.
Ah, I see.
At moderately loud volumes, the distinct peaks of activity on our security monitors smear out into one giant flat plateau. If the rate place model were true, our ability to perceive pitch would completely disintegrate at loud volumes because the map becomes illegible. But human behavior proves otherwise. You can clearly hear the melody of a bass guitar at a deafeningly loud rock concert.
Okay, so the brain isn't just looking at the place that is firing fastest. What about the interval model? How did that try to solve the problem?
The interval model completely ignores the place on the membrane. Instead, it focuses purely on time, specifically the time interval between the electrical spikes. When a sound wave pushes the basilar membrane up, it triggers a spike. The nerve fibers tend to phase lock. They fire in sync with the physical peaks of the sound wave.
Right.
The interval model suggests the brain acts as a massive timing calculator. It looks at the gaps between spikes across all the active nerve fibers. It finds the most common time interval and converts that into a frequency. The most common interval for those harmonics corresponds exactly to the missing fundamental.
It's like finding the lowest common denominator in a fraction. That also sounds elegant. Why does it fail?
It fails because it cannot explain why human beings are so much better at discerning the pitch of resolved harmonics compared to unresolved harmonics.
I need a refresher on resolved versus unresolved.
Think back to the cochlear filters we just discussed. Low-numbered harmonics, like the second, third, and fourth overtones, are spaced far apart in frequency. They fall into distinct, separate filters on the basilar membrane. The cochlea can resolve them as individual peaks.
Okay, that makes sense.
But high-numbered harmonics, like the 15th, 16th, and 17th overtones, are packed very closely together. Multiple harmonics cram into a single biological filter. They are unresolved.
They blur together.
Yes. Psychophysical tests show that if you ask a human to identify a pitch using only resolved harmonics, they are highly accurate. If you force them to use only unresolved harmonics, their performance plummets. It sounds muddy and ambiguous. But the purely mathematical interval model works perfectly well for unresolved harmonics. If the interval model were the whole truth, humans shouldn't have a problem with unresolved harmonics.
So the rate place model fails at loud volumes, and the interval model fails to explain the resolved and unresolved discrepancy. We need a Goldilocks model, something that combines the physical place on the membrane with the precise timing of the spikes.
Which is exactly the breakthrough proposed by Sedolin and Delgut, the spatiotemporal model. They realized that the physical wave traveling down the cochlea has a very specific property. As the wave approaches the best place for a specific harmonic, its phase changes incredibly rapidly. It slows down and bunches up. Because of this, the timing of the nerve spikes will shift dramatically over a very short physical distance.
I'm trying to visualize this. Let's imagine a football stadium. The rate place model is like looking at a single section of fans to see if they are cheering the loudest. The interval model is like closing your eyes and just listening to the rhythm of the clapping across the whole stadium. What is the spatiotemporal model doing?
The spatiotemporal model is watching the fans do the wave.
Oh, okay, let's play this out. If the brain is looking at the wave, it doesn't care how loud any individual fan is cheering, so saturation doesn't matter. The fans can be screaming at maximum volume, but the brain is focused on the movement. It is comparing one fan to the person sitting immediately next to them, measuring the exact microsecond delay as the standing up motion ripples down the row.
That is a brilliant translation of the biology. Sedolin and Delgut modeled a hypothetical neural circuit that does exactly this. It's called the mean absolute spatial derivative, or MASD. It relies on lateral inhibition. A neuron in the brainstem compares the precise firing time of a nerve fiber coming from, say, seat 50 in the stadium with the firing time of the nerve fiber coming from seat 51. It calculates the spatial derivative, the difference across space.
And when they ran this mathematical model of the wave, what happened?
The MASD model produced incredibly sharp, distinct peaks exactly at the frequencies of the resolved harmonics. And crucially, it worked perfectly at high sound levels where the overall firing rate was completely saturated. Because, as you said, even if everyone is cheering at maximum volume, the relative timing of the wave still moves at a measurable speed. It solved the loud volume problem, and it successfully proved why resolved harmonics provide much clearer pitch cues than unresolved ones.
That is incredible. But wait, how do you actually prove this physiologically? To map the wave in a living ear, you'd have to stick thousands of microscopic electrodes into a living cochlea at perfectly spaced intervals to record the neighboring nerves simultaneously. That's physically impossible.
It is entirely impossible with current technology. So to prove their model on living tissue, Sedlin and Delgut used a masterful mathematical trick based on the physics of the cochlea, known as local scaling invariance.
What is scaling invariance?
Because the cochlea is structured logarithmically, the mechanical response of the basilar membrane essentially just scales up or down depending on the frequency. What this means in practice is that playing a complex tone with a shifting fundamental frequency to a single nerve fiber is mathematically equivalent to playing a static complex tone to a whole array of differently tuned nerve fibers.
Let me make sure I follow. Instead of trying to measure 100 different seats in the stadium simultaneously while the band plays one song, they aimed one electrode at one single seat and then made the band play 100 different variations of the song, shifting the pitch up and down.
Exactly. By systematically shifting the stimulus, they force that single nerve fiber to experience the acoustic energy as if it were situated at different physical locations along the cochlea relative to the harmonics. They simulated a spatial array by using a temporal shift, and their physiological recordings in anesthetized cats perfectly matched the predictions of the MASD model.
They proved the brain is calculating the spatial derivative of the phase wave. That is mind-blowing. Okay. So this spatiotemporal calculation, looking at the microscopic timing differences between neighboring fibers, works wonders for decoding the pitch of a voice or an instrument. But it turns out microtiming is just as critical for a completely different survival skill, figuring out where sound is coming from in three-dimensional space, specifically figuring out if the sound is above you or below you.
Yes. Locating a sound on the horizontal plane, left versus right, is relatively straightforward. Your brain just compares which ear heard the sound first and which ear heard it louder. But elevation up versus down is much trickier. If a bird chirps directly in front of you or directly above you, the sound hits both ears at the exact same time. So the brain needs a different cue. This brings us to the research by Lopez Poveda, Alves Pinto, and Palmer on spectral notches.
We talked about notches earlier when discussing the noise masking experiment. But in that case, the scientists created the notch for the computer. In real life, our own bodies create notches, right?
Yes, specifically the pinna, the visible, fleshy, folded part of your outer ear. The pinna is not just a funnel, it is a highly complex acoustic reflector. When a sound wave travels toward your head, some of the wave goes directly into your ear canal. But a portion of the wave hits the ridges and folds of your pinna, bounces off, and then enters the ear canal.
And because that bounced wave had to travel a slightly longer physical path, bouncing off the cartilage, it is slightly delayed compared to the direct wave.
Precisely. And when a direct wave and a delayed wave combine in a tight tube, like the ear canal, they create destructive interference. At very specific high frequencies, the peaks of the direct wave perfectly align with the troughs of the delayed wave, and they physically cancel each other out. They create a spectral notch, a sharp drop in acoustic energy.
So a chunk of the sound is just deleted. And because the shape of the ear is complex, if the sound comes from above me, the wave hits the folds at a different angle than if it comes from below me. The bounce path changes, so the frequency that gets deleted changes.
Correct. If a sound comes from 0 degrees elevation, the notch might be carved out at 8,000 hertz. If the sound source moves up to 30 degrees elevation, the notch might slide up to 10,000 hertz. Your brain tracks the specific frequency of this missing energy to calculate the elevation of the object.
It maps the void. But here is where we hit another paradox. How does the auditory nerve tell the brain where the void is? For a long time, scientists assumed it was just a simple rate profile. The brain looks at the 8,000 hertz nerve fibers and sees they are firing slowly, while the 7,000 and 9,000 fibers are firing rapidly. The brain spots the dip in the firing rate.
But we just established in the previous section why a simple rate profile fails.
Saturation.
Exactly. High spontaneous rate nerve fibers, which make up the vast majority of the auditory nerve, saturate very quickly at moderate sound levels. As the volume increases, their tuning curves broaden, and they lose their sensitivity to small dips in energy. So if the brain purely relies on an average firing rate to find the notch, our ability to detect elevation should just get progressively worse and worse as the sound gets louder.
But I'm guessing human performance doesn't actually degrade like that.
It doesn't. Psychophysical tests reveal a very strange non-monotonic pattern. Human ability to detect these high-frequency notches is excellent at quiet volumes. It gets inexplicably worse at medium loud volumes around 70 to 80 decibel.
Oh, weird.
But then, as the volume gets even louder, performance magically gets better again. A simple rate profile model cannot explain this V-shaped performance curve.
To figure out what the nerves were actually doing, Lopez Poveda and his colleagues recorded from 106 individual auditory nerve fibers in guinea pigs. They played broadband noise, both with and without these spectral notches carved into them. Then, they used a statistical equation developed by a scientist named Siebert to predict the psychophysical performance, to predict what the animal should be able to hear based purely on the discharge rate of the nerves.
And when they set the analysis time window in their model to the full 110 millisecond duration of the stimulus, effectively averaging the firing rate over the entire sound, which mimics the old rate profile theory, the model failed spectacularly. The prediction showed performance getting progressively worse as volume increased. It completely failed to capture that weird V-shaped human performance.
So the brain isn't just taking a long average. What did the researchers change in the model to make it work?
They started chopping the analysis window into smaller and smaller slices of time. They realized that the brain isn't looking at the total spike count. The brain is sampling the nerve activity in extremely brief, discrete windows. When they modeled the brain analyzing the discharge rate in tiny, non-overlapping time windows of exactly 8.6 milliseconds, the predicted performance curve morphed.
Wow.
It perfectly matched the weird, non-monotonic human data. The correlation peaked precisely at an 8.6 millisecond sampling window.
I need to stop and push back on this. We are talking about notches that exist at 8,000 to 10,000 hertz. That means the sound wave is vibrating 8,000 times per second. A nerve fiber physically cannot fire that fast. The biological limit for phase locking, where a nerve fires in sync with the sound waves, cuts off around 4,000 or 5,000 hertz. The nerve simply can't recharge fast enough. So if the nerve can't sync to the frequency, how is an 8.6 millisecond timing window helping the brain decode an 8,000 hertz notch? This is one of the most elegant discoveries in the field. You are entirely correct that the nerve cannot track the fine structure, the actual physical vibrations of an 8,000 hertz wave.
Yeah.
But the nerve isn't tracking the wave itself. It is tracking the envelope of the basilar membrane excitation.
Explain the difference between the wave and the envelope. Imagine broadband noise as a carrier wave that is constantly, randomly fluctuating in amplitude. It gets louder, quieter, louder, quieter. The cochlear filter located at 8,000 hertz isolates a narrow band of that noise. What comes out of that filter is an 8,000 hertz tone that is constantly swelling and dipping in volume. The nerve cannot track the 8,000 vibrations per second, but it can track the slower swells and dips in volume. The outline of the volume changes is the envelope.
Let me try an analogy. Imagine a hummingbird flapping its wings 80 times a second. My eye can't track the individual wing beats, it's just a blur. But if the hummingbird slowly bobs up and down as it hovers, my eye can easily track the bobbing. The wing beat is the fine structure. The bobbing is the envelope.
Exactly. Even at high sound levels where the average discharge rate of the nerve is completely saturated and flatlined, the nerve fiber can still phase lock to the low-frequency envelope fluctuations. It fires slightly more when the envelope swells and slightly less when it dips.
So how does tracking the hummingbird bobbing tell the brain about the spectral notch?
The researchers hypothesized that the exact pattern of the envelope fluctuations, the speed and depth of the bobbing changes depending on whether the nerve filter is sitting inside a spectral notch or outside of it. The fibers tuned near the notch see a different statistical distribution of amplitude modulation.
And the brain decodes this by taking rapid-fire 8.6 millisecond snapshots of the fluctuation. It doesn't look at a long exposure blur of the whole sound. It chops the signal into temporal micropackets and compares the envelope statistics across different frequency channels.
Precisely. High-frequency spectral notches are not encoded by a simple drop in the average rate profile. They are encoded by these dynamic short-term rate measures. The brain is sampling amplitude modulation at a blistering pace to calculate the angle of the sound source.
Okay, let's take a breath and review where we are. The physical cochlea has staggered the arrival of frequencies. The outer hair cells have tracked instantaneous frequency to dynamically suppress off-target noise. The spatiotemporal network has calculated a spatial derivative of the phase wave to extract the missing fundamental pitch. And the nerves have chopped the high-frequency envelopes into 8.6 millisecond packets to map elevation. All of this has happened inside the ear and the auditory nerve. Where does all this intensely processed information go next?
It travels up the auditory nerve bundle and hits the first major relay station inside the brainstem, the cochlear nucleus. This is the grand sorting office of the auditory system.
And this brings us to the research by Stephen Bleek and Ian Winter, who focused on a specific subdivision called the ventral cochlear nucleus, or the VCN. Up to this point, we've been talking about neural spikes as if they are these perfectly reliable, pristine digital pulses. We assume that if the ear sends a signal, the brainstem receives it exactly on time, like a ticking clock. But the biological reality is much messier.
It is absolute chaos. If you stick a recording electrode into a neuron in the VCN, you find an immense amount of variability. These neurons do not act like metronomes. They are constantly bombarded by biological noise.
What exactly is biological noise? Where does it come from?
It comes from everywhere. The basic resting voltage of the cell membrane randomly fluctuates due to thermal noise and ion channels randomly opening and closing. The neurotransmitter vesicles, the chemical packets that jump the gap between nerves, vary in size and quantity.
Oh, wow.
The exact arrival time of the incoming spikes from the auditory nerve has microscopic jitters. Even the physical location of where the synapse connects to the dendrite changes how much voltage reaches the main cell body.
It sounds like trying to transmit a delicate Morse code message while standing on a small boat in the middle of a hurricane. How does the brainstem pull any reliable, mathematically consistent information out of a system that is fundamentally plagued by random noise?
For decades, neuroscientists tried to tame this chaos by categorization. They took the interspike interval histograms, the data showing the time gaps between nerve firings, and tried to force them into rigid mathematical boxes. They used dozens of different complex probability functions, normal distributions, log normal, exponential, gamma, Weibull functions.
Right, trying to make it fit a pattern.
They wanted to prove that neuron A was definitively a chopper cell, and neuron B was definitively a primary-like cell, each with a distinct, rigid statistical shape.
Because science loves putting things in neat little labeled boxes. It makes the textbook easier to write.
But Bleek and Winter took a completely different, much more elegant approach. They looked at the sheer volume of independent noise sources bombarding the neuron, and they realized they didn't need to categorize the noise. They could utilize a statistical law called the central limit theorem of extreme value distributions, or the GEV.
I'm going to need a deep breakdown of an extreme value distribution.
Let's look at the physical event of a neuron firing. A neuron only fires an electrical spike when its internal voltage rises above a very specific high threshold. Below that threshold, the voltage is bubbling and fluctuating wildly due to all that biological noise we mentioned. But the spike only happens when the voltage breaks the ceiling. Relative to the messy baseline, the spike is an extreme event.
Okay, I have an analogy for this. Imagine an overflowing bucket left out in a massive storm. We want to know exactly when the bucket will spill over. The traditional neuroscience approach was trying to measure every single variable, the volume of every raindrop, the angle of the wind gusts blowing water in, the microscopic leaks in the plastic. It's too complex.
Exactly.
The GEV approach says because there's so many random factors interacting, the statistical laws of large numbers take over. We don't need to model the raindrops. We just need to mathematically model the extreme event of the spill.
That is a brilliant translation of the theorem. When a system is driven by a massive number of independent, identically distributed random variables, the ultimate extreme event, the spike or the spill, converges toward a predictable, generalized mathematical shape. The sheer complexity of the noise actually simplifies the macro behavior of the system.
The chaos mathematically cancels itself out into predictability.
Yes. The spike generating process takes on the form of a Markov process. This is a property where the system is memoryless. The probability of the next spike happening depends entirely on the time that has elapsed since the very last spike and the current level of excitation. It completely ignores the long, convoluted history of everything that happened before that last spike.
So when Bleek and Winter applied this GEV mathematical model to the actual living neurons in the VCN, did it work?
It worked beautifully. They analyzed 1,867 histograms from 877 different neural units in the guinea pig VCN. The GEV distribution fit the data with remarkable accuracy, but more importantly, it allowed them to map out how the neuron's firing probability dynamically morphed during a single 50-millisecond sound stimulus.
So what does this mean for our understanding of the brainstem?
It shatters the idea of rigid, boxed categories for neurons. It proves we shouldn't view the VCN as a collection of static, single-purpose machines. Instead, these neurons exist in a continuous, fluid parameter space. A single neuron changes its behavior dynamically. As it adapts to the incoming sound, as it recovers from suppression, its statistical profile goes on a journey through parameter space. The noise isn't a bud preventing the brain from hearing clearly. The noise is the mathematical foundation that allows the neuron to be incredibly flexible and predictable in how it encodes sound.
That is a staggering shift in perspective. But let's take these elegantly chaotic, fluid brainstem neurons out of the sterile, perfect conditions of the laboratory. What happens to the VCN when we throw it into the real world, like into that massive cavernous cathedral we talked about at the beginning of the show?
That is precisely what Mark Sales and his team investigated in their paper on reverberation and pitch in the VCN, the cathedral effect.
Because in a laboratory, you are playing sound straight into a headphone. In a real room, you have reflections. If I speak to you in a hallway, my voice goes straight into your ear, but it also bounces off the floor and hits your ear 10 milliseconds later. It bounces off the wall and hits your ear 20 milliseconds later. It bounces off the ceiling and hits 30 milliseconds later.
Reverberation is a nightmare for signal processing. Those millions of delayed reflections are added back to the direct sound wave, but with completely random phase shifts.
Explain what that does to the physical shape of the sound wave.
It effectively acts as a low-pass filter on the temporal envelope. Remember the hummingbird bobbing? Reverberation fills in the dips. It washes out the sharp peaks and deep valleys of the amplitude modulation. It smears spectral transitions across time, turning crisp, distinct fluctuation into a muddy, continuous roar.
So Sales and his team wanted to see how the fluid parameter space of the VCN handles this muddy roar. How did they simulate it?
They played frequency-swept harmonic complexes, similar to the sweeping pitches we discussed earlier to guinea pigs, but they created two conditions. First, the dry condition, which simulated an anechoic chamber with 0 echoes. Then, they took those same sweeps and computationally convolved them with impulse responses recorded in a highly reverberant corridor.
Wait, convolve with impulse responses. Break down that audio engineering trick for me.
Yeah.
How do you mathematically put a guinea pig in a hallway?
It's a fascinating technique. If you go into a physical hallway and pop a balloon and record the resulting sound, you capture the exact acoustic fingerprint of that specific space. You capture the initial crack, followed by the thousands of decaying echoes bouncing off the plaster and tile. That recording is called an impulse response. Convolving is a mathematical process where you take a dry, lab-generated sound, like the frequency sweep, and essentially multiply it against that balloon pop. The math applies the exact echo pattern of the physical hallway perfectly onto the dry sweep.
So they created perfect virtual reality audio for the guinea pig. They simulated standing 32 centimeters away from the sound source, 125 centimeters away, and a massive 500 centimeters down the echoing hallway.
Yes, and then they measured how well the neurons in the VCN could track the fundamental pitch of that sweeping sound. They split their analysis into two groups of neurons, units that responded to resolved low-frequency harmonics and units that responded to unresolved high-frequency harmonics.
Let's recall the difference. Resolved means the low harmonics are spread far apart, so the cochlear filters isolate them perfectly. Unresolved means the high harmonics are crammed together into a single filter, and the nerves have to rely on tracking the beady envelope, the hummingbird bobbing, to guess the pitch.
Exactly, and the results of the reverberation experiment were stark. For the VCN neurons relying on the unresolved harmonics, even a mild amount of reverberation completely destroyed their ability to track the pitch. By the time the simulated distance reached 125 centimeters, the temporal representation was obliterated.
What did the nerve firings look like?
The interspike interval histograms just showed random, uncorrelated noise. Because the reverberation randomized the phase relationships of the high frequencies, the beating envelope was flattened out, the bobbing vanished. Without the envelope, the VCN neurons had no timing cues left to extract the pitch. The bucket was just sloshing randomly instead of spilling predictably.
But what about the VCN neurons relying on the resolved low-frequency harmonics?
They survived. The neurons responding to the low, widely spaced harmonics maintained a robust, perfect representation of the pitch through all the reverberation conditions. Even at 500 centimeters down the echoing virtual hallway, the temporal peaks corresponding to the fundamental pitch remained crystal clear in the nerve firings.
Let's connect this biological finding to a very real human experience. The cocktail party problem. Imagine you are at a crowded, echoing restaurant, and you're trying to listen to your friend across the table while 10 other people are talking loudly around you.
To solve the cocktail party problem, to segregate your friend's voice from the interfering voices, your central auditory processor heavily relies on differences in pitch. If your friend's voice has a fundamental pitch of 200 hertz and the guy talking loudly behind you is at 150 hertz, your brain uses that 50 hertz difference to segregate the audio streams. It locks onto the 200 hertz pattern and suppresses the rest.
But if the restaurant is highly reverberant, and my brain is trying to use the unresolved high-frequency parts of their voices to figure out the pitch,
You are out of luck. The echoes smear the high-frequency envelopes. The pitch representation in your VCN disintegrates into random spikes. Your brain loses the 200 hertz anchor, it can't segregate the streams, and all the voices collapse into an unintelligible mush.
but because the resolved low-frequency harmonics survive the echoes, we can still scrape by if we focus our attention on the deeper, lower parts of the voice spectrum. The bass frequencies literally punch through the echoes intact.
Precisely. It proves that under reverberant conditions, temporal pitch information is strictly limited to the low-frequency channels. The VCN leans heavily on the resolved harmonics to save us from the echoes.
So the ventral cochlear nucleus is our champion for pitch and timing and echo fighting. But there is another distinct half to this brainstem complex, the dorsal cochlear nucleus, or DCN. And it turns out the DCN isn't really interested in pitch at all. It is hunting for something completely different.
This brings us to our final paper by Sharba Bandiobathe, Eric Young, and Lena Rice. While the VCN handles the what of a sound, the DCN is deeply involved in the where. It handles localization in 3D space.
Which links back to the spectral notches from the pinna, the missing frequencies that tell us elevation.
Exactly. The brain needs a dedicated processor to find those tiny notches. And the principal cells in the DCN, known as type phi neurons, are built for this. But they are incredibly bizarre and highly nonlinear. They don't just receive straightforward excitatory input from the auditory nerve. They also receive massive inhibitory input signals that tell them to stop firing from neighboring cells called type 2 neurons, which are tuned to slightly different frequencies.
So there's a constant neural tug-of-war happening, excite versus inhibit.
Yes, and on top of that acoustic tug-of-war, the DCN also receives somatosensory input.
Somatosensory, like physical touch and body position. Why would the hearing center of the brainstem need to know about body position?
Think about the animal model they use. Cats. Cats can physically swivel their ears, their pinny-like radar dishes, to track a sound. If the spectral notch created by the ear fold changes based on elevation, but the ear itself is constantly rotating, the brain's coordinate system is constantly shifting. The brainstem needs proprioceptive information. It needs to know the exact physical angle the ear is currently pointed to, calculate the audio math correctly. The DCN merges the acoustic data with the physical muscle data.
That is astonishing. It's a cross-sensory math engine. But because these type PE neurons have this massive, nonlinear tug-of-war of excitation and inhibition, you can't just play simple, pure tones to figure out what makes them tick.
Exactly. Traditional models failed to predict how these neurons would respond to complex, real-world sounds. The researchers realized they needed to find the optimal stimulus. Out of all the infinite possible shapes a sound wave could take, what specific acoustic shape makes a type 4 neuron fire the absolute fastest?
How do you search infinity? You can't just play millions of sounds manually and hope you stumble upon the perfect one.
You use an algorithm. They generated something called random spectral shape stimuli, or RSS. Imagine a sound composed of dozens of pure tones grouped together into narrow frequency bins. The algorithm continuously, pseudo-randomly fluctuates the volume of each individual bin, so the overall shape of the sound is constantly bubbling and shifting in real time.
Okay, so the sound is constantly morphing. How does the algorithm know if it's getting closer to the optimal shape?
They used a mathematical tool called a Fisher information matrix. While the sound is bubbling, they're recording the neuron's firing rate. The Fisher information matrix analyzes the variance. It essentially calculates the gradient of the response. It maps out which specific changes in the sound's shape cause the firing rate to increase and which changes cause it to decrease.
It's essentially playing a biological game of hot or cold with the neuron. If boosting the 8,000 hertz pin makes the neuron fire faster, the algorithm says hot and boosts it more. If dropping the 7,000 hertz pin makes it fire faster, it drops it more.
That is a perfect description. It is an iterative feedback loop. The algorithm continually updates the sound based on the gradient, walking up the mathematical hill until it reaches the peak. After about an hour of this continuous hot or cold feedback loop, the algorithm converges. It locks onto the exact spectral shape that maximizes the neuron's response.
And what was it? What is the ultimate trigger for a DCN type 5 neuron? It wasn't a pure tone. It wasn't just a broad blast of noise.
It has a spectral edge.
A spectral edge. Break that down physically.
For many of these neurons, the absolute optimal stimulus was a sound that had very little energy just below the neuron's best frequency, and then abruptly, sharply jumped to high energy exactly at the best frequency. A steep, rising cliff of sound.
And why is that specific shape so important? Let's connect it back to the pin and notches.
Think about the shape of a spectral notch. It is a deep, sudden drop in energy, followed by a steep, sudden rise in energy as the notch ends. The rising cliff of the optimal stimulus perfectly matches the upper frequency edge of a pin and notch.
Oh. Because of that neural tug-of-war we mentioned, the inhibitory neurons are tuned just below the best frequency. So if the sound has a notch, if it's quiet just below the best frequency, the inhibitory neurons stay quiet. They don't pull back on the reins. Then the sound abruptly jumps in volume right at the best frequency, blasting the excitatory input. The neuron is unleashed and fires wildly.
Precisely. The complex wiring architecture of the DCN creates a dedicated feature extractor. When the pinna carves a notch into the sound, the upper edge of that notch acts as a key, unlocking this specific neuron. The dorsal cochlear nucleus is essentially an array of highly specialized edge detectors.
This is exactly like how the visual cortex works. We have specific neurons in the back of our brains that don't care about color or broad light. They only fire when they detect a stark vertical line or a sharp border between light and shadow. The auditory system has built the exact same concept, but for frequency.
Yes. By detecting these spectral edges with extreme nonlinear sensitivity and combining that data with the physical posture of the ear, the DCN provides the higher cortex with the precise, calculated coordinates needed to map exactly where sound is originating in 3D space.
This has been an unbelievable journey. We started with the physical, staggered racetrack of the cochlea, where sweeping sounds physically compensate for the mechanical delays of the fluid.
We moved to the outer hair cells, acting as a dynamic built-in compressor, calculating instantaneous frequency to suppress off-target noise and dynamically widen or sharpen our auditory filters.
We looked at the pitch paradox and how the brain uses a spatiotemporal network to measure the microscopic speed of the phase wave rippling across the membrane to lock onto a fundamental pitch that doesn't physically exist.
We discovered that the auditory nerve chops the signal into 8.6 millisecond packets, tracking the low-frequency envelope of high-frequency noise to decode elevation.
We watched the ventral cochlear nucleus mathematically filter the absolute chaos of biological noise into predictable extreme events, while desperately clinging to resolved low-frequency harmonics to fight through the smeared echoes of a reverberant hallway.
And finally, we saw how the dorsal cochlear nucleus employs a massive tug-of-war of excitation and inhibition to act as a flawless spectral edge detector, integrating sound and body position to map our world.
The overarching theme here is that the microphone analogy is dead. Your ear is not a microphone. But this massive web of active, predictive calculations leaves me with a profound, lingering question. If our brain expects and physically requires this incredibly messy, delayed, nonlinear, suppressed, chaotic biological signal to decode reality, what happens when we try to bypass the biology?
You're thinking about brain-computer interfaces.
Exactly. We have companies right now trying to build neural implants that pipe audio directly into the auditory nerve or the brainstem.
Yeah.
But if an engineer feeds the VCN a perfect linear 44.1 kilohertz digital audio file, a signal without the cochlear delay, without the two-tone suppression, without the biological resting noise, will the brain even be able to understand it? Or will the brain reject a perfect digital signal precisely because it lacks the organic chaos it evolved to calculate? If the brain expects a sculptor, what happens when we just hand it a photograph?
It is the ultimate frontier of auditory neuroscience. If we don't replicate the chaos, we might not replicate the hearing.
It is something to chew on. The next time you effortlessly pick out your friend's voice in a loud, echoing room, take a moment to appreciate the billions of spatiotemporal calculations your brain just executed in a fraction of a millisecond to build that reality for you. Thank you for joining us on this deep dive into the hidden world of sound. We'll see you next time.